Welcome to my session about what the CRaC coordinated restore at checkpoint on the Java virtual machine. All right, so let's get it started. First, I'm Gerrit Grunwald. I'm working for Azul Systems as a developer advocate. I'm mainly interested in all things Java. It was a lot of front-end in the past, and these days it's more about backend and JVM related stuff. Okay, so just up front, if you would like to get the slides, you can take the screenshot of this QR code and then you will find it at slideshare.net. And so I give you a second to make a screenshot if you like. Otherwise, I think there will also be a link from the organizers. All right, so Java is great. I mean, it has a vibrant community, as we can see with this conference here. And we have hundreds of Java user groups. We have thousands of free open source software projects. But the real star of the whole thing is the Java virtual machine, right? So I think we can all agree on that. But the question is, how does it work? I mean, let me give you a very simple introduction on how the JVM works. And so we start with our Java source code file that you write in your IDE or your editor or whatever. Then it gets into the Java C compiler, which creates a so-called class file out of it. And this class file contains cross-platform bytecode. That means as long as you have a JVM on your platform, you can run this code from the class file. So then we take the class file, use the class loader, and load this class file into the JVM memory, which is already part of the JVM, as also the class loader is. So once it's in the JVM memory, then it gets into the so-called execution engine. And you can already see that the execution engine contains multiple parts, right? And we will take a closer look to some of them. So if we zoom a little bit in, then we see we have the interpreter, we have the C1 JIT compiler, which is formerly known as the client compiler. And then there's the C2 JIT compiler, formerly known as the server compiler. And we have a profiler and we have a garbage collector here. So in this session, we will only focus on the first three parts here. And just a few words on the client and server compiler. This have been merged into the JVM from JDK 8, as far as I remember. So from that moment on, we had C1 and C2 in the JVM. Before that, you could change the compiler. You can say, I would like to run it on the client compiler or on the server compiler. Okay. So we have the code from the class file in the execution engine. The first thing that happens, the interpreter takes the code line by line and really converts it into the instruction set of the CPU. And the JVM is watching that and it's counting method calls in this code. So once a specific threshold is reached, it will take the code and then pass it to the C1 JIT compiler. And this C1 JIT compiler compiles very quickly code into native code, but with low optimization. And the reason for that is, I told you already, it's the formerly known client compiler. And you can imagine that if you, for example, run IntelliJ or Eclipse or NetBeans, which are all desktop applications written in Java, running on the JVM, and you double-click the icon, then you would like to get it started as soon as possible, right? So that's the reason why the C1 JIT compiler is really just fast. Not a lot of optimizations, but really getting you to the point of execution as fast as possible, which is good. And once again, this compiled code from the C1 compiler is running and the JVM is profiling it. And again, figuring out how often specific parts of the code have been called. So again, like method counting. And once another specific threshold is reached, it will take this hot code and pass it to C2 compiler, which is formerly known as compiler, more complex, and creates a much better optimized code, but it's also slower because it does all these optimizations and that takes longer, right? So in the former times where it was the server compiler, where we have the monoliths, so it was not really that big of a problem if the JVM takes some time to start up and do all the optimizations before the application on your server is running fully optimized. So that's the reason we have the C2 JIT compiler. So it means hot code from the C1 gets into C2 compilation. And once it's there, it will be optimized, and then it will be very fast. Okay, this whole thing, so we're having these two compilers. In one is so-called tiered compilation, and we have different levels of execution here. So that means the interpreter, for example, has level 0, and then we see the C1 compiler has 3 different levels, and then the C2 compiler has level 4. And the reason for these 3 different levels in C1 is not so hard to understand, because if you know where it's coming from the client side, so from the client compiler, you can imagine that once you get your application running and it's perfectly and you build it so that you probably don't need profiling, right? Which means the execution is even faster. But if you need, for example, profiling, then it has to create all this profile information, might get a little bit slower then, right? So that's the reason we have the different levels in C1. And the preferred way of doing this transitions is we first interpret the code level 0, and then if possible, put it into C1. And if this is then done, then we go to C2. This is usually the way it works in the JVM. There are other transitions between these levels, but we just take this as the standard for now. And that leads me to the execution cycle, which is in principle the same that I told you before. So we start with the interpretation, which is slow, execution level 0. And then there's the profiling phase, finding hotspots. And this is also the reason for the name of the hotspot compiler. And then once we have the code that needs to be compiled, we put it into the C1 compiler, which is fast compile, low optimization, level 3. And then another profiling phase to find the hot code from the C1, and then it will get into the C2 compiler, whereas high optimization takes a little bit longer to compile. And then you see this missing thing there, which is the so-called deoptimization. So this can happen, and then if it happens, it's a performance hit. So let me give you a short information about deoptimization here. If we take this block of code, which is a simple if then else a loop, right? So we just check if the value is greater than 0, then the result should be true. It should be 3. And if not, the result should be 0. So this is the code that we take a look at it. And then if we profile the code and the JVM figures out, wait, most of the times the result was 3, means the value was most of the times greater than 0, then it optimizes the complete block to something like this. It just says the result equals 0. That's the result. And this is guarded in the JVM. As long as this value is larger than 0, then just the result is 3. So if we now pass in a value equals 3, then this is true, means we return result 3. If now, for whatever reason, we pass in a value that equals 0, then suddenly this optimized code is not valid anymore. So that means we compile the code in C1 and C2 and optimize it and just say the result is always 3. But suddenly the whole thing is not true anymore. And then we need to take this optimized code, throw it away, and then go again to interpretation, C1, C2. And you can imagine that this really is a performance hit, because that means the already optimized code suddenly needs to be de-optimized, needs to go through the whole cycle again, and that takes some time. So that's all great, but it takes time, okay? So it's not for free. And if we take a look at a JVM performance graph that is here leveled by 1, then we see these 3 different colors here, which is yellow is the interpretation phase, and then the green part that you see there is the C1 and C1 profiling phase, and then the blue part is the C2 compiler. You already see that the C2 is, it doesn't take forever to get into the C2 phase, right? So it's fast to get there. But then this is usually the time that we define as the JVM startup. And this is it's a tricky thing to say JVM startup, because if you really take a plain JVM, you create one class and just say hello world. If you measure the startup time of this JVM, it's probably within milliseconds. So if we talk about JVM startup, what we mean mainly, or most of the people mean, is the JVM warm up. right? Because it depends on the application of your application. The classes have to be loaded, compiled, and all that. So this is your code. And this is usually what people mean if they say JVM startup is slow, because they're getting to the point where their application is fast, just takes some time. Okay, so then we see these periodic gaps here. This is usually garbage collector pauses where we have stopped the word garbage collection, means there's at that point a performance hit, and then you will see that. But the other thing is these really large gaps in this warm-up phase, and this is the de-optimizations. So that means at the error, the code was already optimized, suddenly something happened, and then it has to de-optimize and optimize again, right? So, and at one point, you see this, we don't see this de-optimizations anymore because the code is then up and running like it should. Okay, so if we take this knowledge to a microservice environment, then you would see probably something like that. You have the first run, you have the JVM startup, including the warm-up. Second run, same thing. Third run, same thing. Well, that could be a problem. I mean, it's not for everyone a problem, but some people really suffering from JVM startup time in microservices. And wouldn't it be great if you can do something like this? You just start it up the first time, you warm up the JVM, second time you start it, it's fast, third time, fast. From that moment on, there wouldn't be any startup overhead. That would be really great. So let's take a look at the possible solutions that could us help in this case. First of all, there is something called class data sharing, or CDS, which is not really related to JVM warmup, but people came up with that, and so I added it to the slides to give you at least an idea what it can do. So it's there is app and dynamic CDS, and in principle, it's a dump of internal class representation into a file, and these representations will be shared on each JVM start, which is the CDS. But that also means there's no optimization or hotspot detection here, because this is just class loading, right? So that really reduces the loading time of classes, because you have to think about it's like an optimized way to load classes. And this optimizations will be stored in a file, and then the next time this class is needed, it will just take it from this optimized file. This is the idea. And this could reduce the startup time up to 1 to 2 seconds. It really depends. And it's also configurable. So there are sessions just about CDS and how to optimize it. And this is already per default is enabled since JDK 12. So you might even use it without knowing it. But still, there are ways to optimize that. And like I said, it can give you a faster startup depending on how many classes you have to load. And just keep in mind, CDS happens here. So that means during the class loading period, and it's even not into JVM memory at that time, right? This is the way it gets into JVM memory. And after that, we have all this interpretation C1, C2 phase. So that means it's not really related to compiling and optimizing and reducing that part that I defined as the JVM startup time. Okay. And then there's this other thing called ahead of time compilation. You probably heard of that, shortly just AOT. And why not use AOT, right? So we don't have to interpret bytecodes here. There's no analysis of hotspots needed, no runtime compilation of code. We can start at full speed straight away, and GraalVM native image does that. So problem solved, right? Well, not so fast. AOT is by definition static. So that means the code is compiled before it is run, and the compiler has no knowledge of how the code will actually run. Well, and there is something that could help, which is called profile guided optimization, or PGO. And this can partially help. That really depends. There is not really something where you can say this will always give you the full performance. It really also depends on your application. And if we take again a look at the JVM performance graph, then I try to, because you can't really measure that. There is no general rule that it's always like this, but usually you can say you can at least get up to 60% of the JIT compiled code of the speed if you just do plain ahead of time compilation. And if you use PGO, so the profile guided optimization, then you can gain even more. You can get up to 90%, and sometimes you can even reach the JIT, but not the whole time, most of the time. So it will get faster. You will get close to the JIT performance, but not really getting there. And to do that, you also need to do some profiling. And as far as I know, in GraalVM, they do it like this. They run the JVM that's coming with GraalVM. That means the JIT, and use the profile from the first run. So you do a run of your application, create a profile, and then you take this profile that you created with the JIT and apply it to the process of creating the native image. And so you get the more optimized code. But still, this is a snapshot, right? So this is not really, if then something changes at runtime, you have no ability to optimize it further from that point of view. So if we take a little comparison between AOT versus JIT, then it means the AOT can make use, a limited use of method inlining. So that means it can't do it at runtime, where the JIT can aggressively do method inlining at runtime all the time. Even if you load code at runtime, you can optimize it further, which AOT really can't do. You don't have runtime bytecode generation in AOT, where in JIT you have, of course, runtime bytecode generation. Reflection is possible in AOT. It's more tricky and it often leads to problems, but it's possible. In the JIT and the JVM, it's pretty simple to do reflection, and we do it all over the place. Then it's just not possible to use speculative optimizations at runtime in the AOT, where the JIT really can do that. This is stuff like branch prediction, for example. So the JIT can figure out if a specific part of the code is called more often, it optimizes this part of the code. And this can even change. So in a later phase, maybe another part of the code is used more often. So it can then change again and do an optimization for this other part. Overall performance usually will be slower than with the JIT. So the JIT will be faster overall. And the biggest problem that I see with the native image stuff, for example, is that the deployed environment is different from the development environment. So I talked to people, they told me they had the problem that, for example, when they run all the tests in the JIT, it's all fine, everything's green. Once they create the native image, it failed. So it's hard to debug these cases, right? It's a different thing. If you create a native image, a native executable just works differently in some parts than the Java code. That's just a fact. Okay, on the other hand, AOT starts with full speed, right? So there's no really startup time that's needed for the JIT. With AOT, you can really just start straight away. There's no overhead to compile code at runtime, where we have the overhead of the JIT. And we also have a really small memory footprint, because the AOT created code just contains the classes that we really need, where the JIT always has the whole thing, even classes that never been used, but part of a library are, for example, they will be part of the whole thing, so will be bigger. So the memory footprint. That means the JIT disadvantages is more or less, it requires more time to start up. The CPU overhead to compile code at runtime is there, and it has a larger memory footprint. Okay. And I found this chart by Thomas Würtinger from the GraalVM team, which also, it's just in principle the same that I told you. It just shows you the differences, where we have the startup speed is the big advantage with the AOT, the peak throughput is the big advantage of the JIT. The reduced max latency, this is related to the garbage collector, which is in GraalVM. I'm not sure they can use G1, but I'm not sure if you can switch, for example, to ZGC or parallel GC or something like that. I think this is not possible at the moment, where you can define that on the JVM, on the JIT, of course. Small packaging, it's more or less the same, but the memory footprint is definitely lower with the AOT. Okay, so that's the base here. And then let's now take a look at a different approach, all right? There is a project called CRIU, which is Checkpoint Restore in User Space. And it's a Linux project, and it's part of the kernel since 2013 already. So it means it's a long time in the kernel. And it freezes a running container or application, and then it checkpoints the state of this application or container to the disk. And then later, and it can restore from this saved data, the application back to memory. So that's the idea. In principle, you can think about, this is nothing really new. You can think about something like, if you have a laptop and you close the lid, and then after an hour, you just open it again, the application and all the stuff will be there, right? So in principle, exactly the same happens there. So Windows can do that, Mac can do that, and Linux can do that too. So that means you close it, the operating system gets the hint, oh, it's some kind of a shutdown here. So just freeze everything and save the state. Once you open it again, it will take the saved state and move it back to memory, and it's already then running when you open it, right? This is the same thing, just on an application base here. Okay. And it's already used. I mean, OpenVZ, Linux containers, Docker, and Podman, they use CRIU already. One thing I have to tell you here is it's already the first line. It's a Linux project. That means there's nothing comparable in Windows or Mac. So this is just working on Linux. And it's mainly implemented in user space. The main goal, like I said already, it's migration of containers from microservices. And it relies on the /proc file system. So that also means there are Linux distributions that don't really use the /proc file system. So then CRIU won't probably not work there. But usually, if you have something like a Debian or whatever, it works with procs. So it can checkpoint processes and threads, application memory, memory map files, shared memory, open files, pipes, FIFO, sockets, inter-process communication channels, timers and signals. And it can rebuild a TCP connection from one side only, so you don't have to do all the handshaking, right? It can do that from one side, which is quite impressive. But as with every project, this doesn't really come without challenges. So first of all, if you would like to restart, you create this state file, right? You checkpoint it, and then you would like to restart from this checkpoint on another machine. You can imagine that this is not that easy, because just think about if you have open files that are not present on the other machine, or you have shared memory, this is not just on the other machine, you don't have that, it won't probably not work. And also stuff like if you have different architectures, you create the checkpoint on an x64 machine and then you would like to restore it on an ARM64 machine, it won't work, of course, right? So starting multiple instances of the same state on the same machine also won't work, because the PIT, that is the process ID, the unique process ID on Linux systems, it's part of this checkpoint. So that means once you restore it, it will probably fail if you do it multiple times, because the PIT is already taken by the first time you restore it. So the second time won't run because the PIT is taken. And yes, you are right if you guess that what happens if the PIT is already taken by another process and I restore it with the same PIT that's already there, it will fail. We are working on a solution for that, and it might probably show up in the future, but at the moment, this will probably fail. And if you apply CRIU to a Java virtual machine, then, I mean, this is, it sounds easy because, oh, the JVM is just an application. I can just checkpoint it and restore it. Well, the difference here is that, for example, if you have the JVM, it's a whole environment. In this JVM, you run your application, and your application is in the end opening sockets, opening database connections, opening files and stuff like that. So if you just now shut down the JVM without telling your application that all this stuff is happening, the next time you restore it, the JVM might probably start, but then it will fail because your application says, oh, wait a minute, I have this file open. No, it's not open anymore. Oh, my database connection, where is it, right? So this is the problems you have to take care about. So that makes it not so easy, which leads me to CRaC. And this means coordinated restore at checkpoint. And the big part here is the coordinated, because this makes it possible, for example, to tell your application that it will be checkpointed or that it was restored, right? That's the big difference here. So what we do is we bundle CRIU with the JDK. So it's a specific version of CRIU that comes bundled with the JDK. The heap is cleaned and compacted. So that means the JVM is in a safe state when we do the checkpoint. And it throws checkpoint exceptions in case you have open files or sockets or other stuff. So you will get an exception if something goes wrong. And it comes with a pretty simple API. We will take a look at that a little bit later. And it creates checkpoints using either code or JCommand. So there's always the question, why can you do a checkpoint in code? Well, it's a good question. Sometimes you have routines where you would like to run stuff, and you absolutely know when I run all this code and test my application with that, then it's warmed up. I know that. So I would like to create the checkpoint exactly at this point in time. And this is good using it from code. The drawback is that once you created the checkpoint, you just would like to do it once, right? So the next, you did the checkpointing, and then you have to go back to the code and just comment out this line, because otherwise it will create the checkpoint every time. And you don't want to do that. But this is the reason why we have it either in code, or you can use JCommand to create the checkpoint. And it uses the JVM save point mechanism. This is in principle the same that is used for stop the world garbage collection. So that means the JVM is the master of everything that's running on it, right? So, and if it does it, for example, it stop the world garbage collection, the JVM can stop all the threads and make sure that everything's now in a safe state. Now I can clean up my heap and then I can restart it, so to say. And we use the same mechanism to create the checkpoint here because this is needed there. This is an OpenJDK project. So, and you can find it under openjdk.org/project/CRaC. And that means it's not really something that is only available in Azul, Zulu, or something like that, because we invented this idea, and one of our engineers, Anton Kozlov, is working on that. But we provided the code as an OpenJDK project because it just makes sense to have something like this in OpenJDK, right? So you can find more information checking out this link. And I already mentioned that. So what we have to do, we have to let the application that is running know the point in time when we create the checkpoint to give you as the developer the ability to react on this checkpoint mechanism. So that means you have the application, I tell you, I will now checkpoint your application, then you can take care about closing resources, closing the database connection, and so on. And then the next time when then the application and the JVM is restored from the checkpoint, again, we let the application know that, hello, you have been restored from a checkpoint, then you can take care about re-establishing the database connection or re-establishing the open file that you need to write or read from. So this kind of stuff, that's the main idea. So these are the restrictions compared to the plain CRIU approach. So that's what I meant, but we have the coordinated restore at checkpoint. So for doing that, we have two runtime parameters for Java, which is the -XX:\CRaC checkpoint 2 equals path. And then you can do -jar, @jar, whatever. So what we here do is you define the path where the JVM should store the checkpoint in case a checkpoint will be created, right? So this is just a parameter that we pass to the JVM. And then in case there is a checkpoint, then the JVM knows where should I store these checkpoint files. And when you restore it, you just point the JVM to this folder and say, please restore it from this folder. And then if it finds something there, it will restore it from there. That's the main idea, to start and restore using CRaC. I already said there is an API, and it's so simple. It's just one. Oh, my keyboard doesn't work anymore. Come on. Ah, there it is. There's just one interface. It's called resource. And this interface only comes with two methods. It's before checkpoint and after restore, which is a pretty simple interface, but that's all it needs, right? So CRaC uses resources that can be notified about the checkpoint and restore. That's what I showed you before. And classes in your application code that implement the resource interface, this will receive callbacks from the JVM to make it possible to react on that, right? So this is the main idea. And this resource objects you need to register somewhere. Somehow the JVM needs to know what are the resource files I need to notify in case of a checkpoint or in case of a restore. And therefore you need a so-called context, right, to do that. And this context you can get by calling core.getGlobalContext, right? It's a static method, and there's only one context which takes care about all the resources that you have in your code. And in the end, it looks like that. You implement the interface in your resource class, which is, for example, a database manager, right? So you implement the resource, you have the two methods before checkpoint and after restore, and then you get the context by core get global context, and then register this resource to the context. That's the main idea. And in the end, what happens then is this context takes care, first of all, it maintains the list of all the resources, right? And then it takes care about the order these resources will be called, because it's important. For example, if you have resources that depend on other resources, you have the database, for example, and then you have another resource that reads something from the database or writes something to the database. That means the database has to be there before you can use the next resource, right? So whatever you have. In this case, you have to make sure that this not only registering the resources in the right order, but if you do the checkpoint, you have to call them in the reverse order to make sure you are back to the point where you all started. And if you call after restore, then it should be in the same order that was also used in the beginning by you. If you registered them, it should be the same. But I will show you that in a minute. Okay. I already mentioned that you can do that either programmatically using core.checkpoint_restore, and I have to say that the name is a little bit misleading here. Checkpoint restore doesn't really mean it does the checkpoint and restore directly. In principle, it just creates the checkpoint, right? So it doesn't really restore it. So no, you can't really do a checkpoint by code and keep the application running. The reason for that is that we use CRIU on the underground to do that in the background. And this is operating system level. So that means it will really take care about shutting down everything and then save the state. And it doesn't make sense to restart it from there. That would mean you have to also restore all the resources and so on. So that means if you create a checkpoint, the JVM is dead after that, right? So this is the reason you just probably do that once to create this checkpoint, and then that's it. And the next time you just start from there. And you can, except from code, you can also do it using J-command to create the checkpoint. Okay, so now let me give you a very simple example, and this should just give you an idea how the whole thing works. So I created a little app, a demo that really just takes, it has a schedule thread that will be executed every 5 seconds, and every 5 seconds it will call a loop, right? And in this loop, which goes 100,000 times, it will check for a random number, again between 1 and 100,000. Is this number a prime number, right? So, and to make it more realistic, we have a cache, and this method first of all checks, is the result maybe in the cache already? And if it's in the cache, it directly returns the result and says, yes, I have it, it's true or false. Okay, that's pretty fast because it's just memory. If it's not in the cache, then we have to calculate this if the number is a prime. And if you have large numbers, this takes some time, as everybody knows. So we calculate, we get the result, we store the result in the cache, and then we return the result, which is slower compared to the plain cache approach because we have to do all the calculation. Okay, that's the normal thing. That's the whole application. Plus, to make it more realistic, the cache, because usually if you have a cache somewhere, that means objects in the cache will time out at some point. You don't want to have the values in your cache forever, right? So at some point you say, oh, this value wasn't called for the last, I don't know, 10 seconds or 1 day or whatever, and then you just wipe it out. So in this case, in the example, the cache will just start after 50 seconds, and then it will forget values that are older than 10 seconds and will just wipe them out. That's the main idea, and this is important when I come to the demo later on. Okay, so that means the first run I run it, it will be pretty slow because the cache is empty. Every random number has to be calculated if it's not in the cache, which is in the beginning the case. And then over time, it should get faster and faster. So the time to do the whole run for the 100,000 numbers should decrease with every run. That's the main idea. And I made some tests on a machine. It was not this one, another one. And there it took around 9 iterations to get into the state where it will be more or less stable. And the reason why it's not a flat line is, of course, because after 10 seconds, then the cache will remove values, then it will be added again, remove, and so on. So it will just level out at some specific point in time. And this is more like applications behave, right? So we'll never reach a perfect state, which is a flat line of performance. It will always be up and down, but it will be level out at some specific level here. Okay. So the demo, instead of doing a demo, usually I do that live on a Linux system, but because on a Mac here, I just created slides. I just give you like 2 shell windows here. On the left shell window, I just start my Java application and I point it to the /CRaC-files folder, and it should store the checkpoints in that folder. That's the main idea. And then I started and I just put in some system out print lines where I just print out the order where I registered the resources. So the first resource I register is the generic cache and then the main class. In this example, it's not really needed to register them. It's just to give you an idea how it works, right? So then the first run, it's pretty slow because the cache was empty and it took around 27 seconds here. This is because it was a really slow machine. On my M1 Mac, it takes around 1 second for the first run, but on this machine, it took 27 seconds. And because it's slow because the cache is not filled. So then the second run, you see it's already faster. The cache has more elements in there. And then we see it gets faster and faster and faster with every run. And at one point, we just decide, okay, let's say it's 17 milliseconds now. Now this is fast. The cache is filled. Let's create a checkpoint. So I go to a second shell window on the right side here and use J command. I call it with the jar file that I started. You can also use the pit to do that. And then the command is jdk.checkpoint. This will then create the checkpoint for us. And you will see on the other side, you will see something like that. So on the right side, you will see it will give us the pit for the process that we stopped. And you see on the left, it's the application will also output the pit so that you can just see it's the right one. And then in the before checkpoint methods here, I just, again, put some system out print lines that you can see that they will be called in the reverse order, right? And then it will create the checkpoint, and then the JVM will be killed, and that's it. Okay, so we are back to the shell then. Now we wait some time, and then we say, okay, now let's restore. So restoring, I told you, is with the -x column CRaC restore from, and then we again pointed to the CRaC files folder where we have the file stored, and then this is what happens. First of all, it gives us in the after restore methods, we see again, this is now caught in the original order. We registered them, the resources, and it continues running with number 12. And it was directly fast, and the cache is already filled, because what happened here is we took the saved state and loaded back into memory. That's all what happened. And because we saved it with the filled cache, it's still filled. And this is now the point where you should maybe ask yourself, how does it work? Because I said the cache will forget the values after 10 seconds. That means if I create a checkpoint and I stop the JVM, and the next time I start it, maybe a minute later, then first time I hit the cache will say, wait a minute, all the values that I have are outdated, and it will wipe out the cache. And this is exactly one of the problems that we have. If you have time-dependent data in your code, you need to make sure that you take care about that. So that means what I did here, when I create the checkpoint, I add a variable and store the current timestamp in epoch milliseconds into that variable. And when I restore the checkpoint, I again take the current timestamps in epoch milliseconds, calculate the delta between the stored one and the actual one, and apply that delta to all values in the cache to make sure these are still valid. And this is something you have to do. And this is probably a drawback because you have to take care about time-dependent stuff. And this is, it could be tricky, but it all depends. Like I said, if we talk about microservice environments, then of course you need to change your code, but usually the microservices are not like this big. They are small, they should be. That means you probably don't have to change a lot of places in your code to make it work, okay? So, and then like you see the next run after 5 seconds, and it will continually running fast. The good thing now is I could even stop the JVM now and restore it again, and it would start again from 12 because this is the state that I saved. So, and that's the really interesting part here, because the main idea you can imagine is this demo is just running on the plain JVM in the shell. But if you think about it, you create your microservice, you deploy it, or you put it into a Docker container, then you start it up in the Docker container, warm it up, create the checkpoint in the image in the Docker container, and then you can use that and restore it from there at startup. So that means the next time you start it up, it will directly start up from the checkpoint. So you don't have to warm up the JVM anymore. That's the main idea. Okay, I already said we can create a checkpoint using J command. You can run it with your jar file or with the pit, or you can use it from code. And I already said, yeah, the name of the method might be a little bit misleading. It does just the checkpoint. It doesn't do the restore here, right? It's just the method is called checkpoint restore. So the question is when to do the checkpoint, right? There is some idea that we have how you can do it. It's just an idea, and we use that, and it works, but this really depends. So what we do, if we do demos, we run the code and we use the parameter -XX column plus print compilation. What it does, it really prints out all the compilations that are going on. That means in the beginning, you see a lot of compilations, but then at one point in time, you see it's getting slower. So you don't see a lot of compilations printed out on the console anymore. That means at that point in time, now all the compilations have been done and the optimization. So that means this might be a good time to create a checkpoint, right? This is just an idea how you can do it. It depends. But to give you an idea where to start, this could be one thing to start from. The demo code is available on my GitHub repository. So if you would like to play around with it, it's the easiest way to just fork it and then play around with the stuff, because then you just don't need to do anything. It will directly work. So that's all great. I mean, I showed you stuff that we did, and I showed you a demo that I did, and everything worked fine. That's cool. But how good is it really, right? Of course, we did not only test with own written small demos. We used some other stuff like Spring Boot. We used Micronaut, Quarkus, and something like an XML transform. And this is the time to first operation that we monitored here. And you see, for Spring Boot, it was around 3.9 seconds, Micronaut 1 second, Quarkus 980 milliseconds, an XML transform 4.3 seconds. This is on the plain OpenJDK. And now if we run it on an OpenJDK, including CRaC, using the checkpoint restore, we came to this times, right? So you see, it's really fast now. And you might wonder that even if the original startup times really have been different, that now they are more or less all in the same range. The reason for that is that we more or less only rely on I/O. This is disk I/O. You just load it from your files back into memory. This is really fast. And the only difference here is if you have a lot of resources that need to be restored, like open database connection, open sockets, open files, even this is always in the range of milliseconds. So it will be fast. And this is the great outcome here. And as a summary, CRaC is a way to pause and restore JVM-based application, and it doesn't require a closed world as with a native image, for example, where this is needed. And the benefit is potentially extremely fast time to full performance level. It eliminates the need for hotspot identification, method compiles, recompiles, and deoptimizations. And we have an improved throughput from the start. And CRaC is an OpenJDK project, so it's nothing done in the secret background, but you can check it out. It's in the GitHub repository. And it can also save infrastructure costs. So you might ask yourself, well, how should it save costs? If you run it on a cluster in nodes, then usually you see, you probably know this kind of graph, right? To have on the y-axis, you have the CPU utilization. On the x-axis, you have the time. And you see this peak in the beginning in the CPU utilization. And usually this is the JVM startup time. And this is more or less the interpretation and compilation overhead that we see in the beginning of the JVM startup, because every class has to be interpreted, C1 compiled, C2 compiled, optimized, and so on. And it just takes CPU because at the same time your application is already running. Okay, so if we now create the checkpoint here, right, where all the stuff has been done already, and then we start the next time from there, then we really save. First of all, we eliminate the startup time, we eliminate the CPU overhead that we had in the beginning. That means the next time you start, you probably don't need that many cores in your nodes, right? Or you don't need that many nodes to get a slow startup time, because this is now directly optimized code that you start. So this is the big advantage, and that can really save some money, because usually it's the multi-core nodes that are really expensive. And also, if you have high power nodes, they are more expensive than the low power nodes with just 1 or 2 cores or something like that, right? So this can really save you money in the cloud. Like I already said, everything is available on GitHub, github.com/CRaC. You will find it there. All the demos that I showed you, the one with Micronaut, Quarkus, and Spring Boot, you can find it there. You can play around with it if you don't believe us. There's also a demo for Amazon Lambdas, because they also suffer from startup time. And there's a wiki page, wiki-openjdk.org/display/CRaC, where you can also get more information. And I did the demo already just in slides. And with this, it's time to say thanks for attending this session. And if you have questions, let me just stop sharing here. And I will go to the chat. So if there are questions, you can either put them into the chat. I will be there a couple of more minutes. Otherwise, just ping me on Twitter. My Twitter handle is @hansolo_, and I will try to answer as many questions as possible. Okay, the GitHub, it's pretty simple. It's GitHub. The question was, could you please publish a GitHub link in chat? It's github.com/CRaC. That's it. There you will find all the information, and if everything else is needed, then just ping me and I will try to answer it. For the demo, it's okay. It's github.com/hansolo. This is the link for the CRaC 4 demo that I showed you. The other demos will be found in the github.com/CRaC repository.